In this video, we present our work enhancing numerical prediction of MLLMs with soft labeling. This work done at Amazon by Pei, Zhao Hao, Davide, and Ashwin. Large language models and multimodal large language models have achieved remarkable progress across various tasks, such as image captioning, visual question answering, and many specialized domains like document analysis, visual grounding, etc. During training, the learning is to predict the next token associated with the factual cross-entropy loss across the token vocabulary, no matter the target is a word, digit, punctuation, or anything else. Although this unified mechanism simplifies the learning across various tasks and it has become dominant, a natural question to ask is the standard cross-entropy loss optimal for any multimodal tasks? In this work, we are investigating the limits of standard cross-entropy loss in an important case, numerical prediction, which is in continuous space. Numerical prediction is a critical capability with many applications in object counting, object localization, chart figure understanding, etc. For example, answering the gross income from a tax report or answering how many trains in a traffic scene, as in this example. Let's assume we have two predictions, A and B, with a posterior probability distribution as shown. Cross-entropy loss measures the distance between the target and the prediction distribution over the token vocabulary, and the target distribution is usually a one-hot vector where the probability on the target is 1 and the rest are zeros. In this case, the wrong prediction to any non-target index can potentially have no difference. Predictions A and B have exactly the same cross-entropy loss because their probabilities on the target, that is 4, are the same, that is 0.3, although their overall distributions are quite different from each other. However, this is counterintuitive. Prediction B of 3 trains should have lower loss than prediction A of 1 train, because the former is closer to the target. The cause of this issue is rooted in the one-hot representation of the target probability distribution, namely hard labeling of the standard cross-entropy loss. So unlike discrete tokens, in numerical prediction, the de facto cross-entropy loss with one-hot encoded target fails to account for the distance between predicted and the target token problem. When prediction is incorrect, we should measure how wrong it is by assessing the distance from the target, rather than treating all wrong predictions equally as long as the confidence on the target token is the same, as is done in hard labeling. To address this problem, we propose soft labeling for the 10-digit token from 0 to 9. Here T is the target, delta is a Dirac delta distribution, and Psi is a probability distribution typically centered at the token with index of T. It can be Poisson, binomial, uniform distribution, so on and so forth. For the final loss, we just compute hard labeling loss for the regular tokens and the soft labeling loss for the numerical tokens. We demonstrate the effectiveness of the proposed soft labeling on virtual grounding, object counting, and chart understanding tasks. There are more interesting visualization results. Thank you.